LPL to go for the final exam. According to the register billing, the final exam date is 13th May, Tuesday from 5:45 to 7:45. So only the final exam is 2 hours exam. Other exam 1 and exam 2 is the class time only, 1 hour 15 minutes. Okay. So I already uploaded these things, and this is the information about this course. This is for grading. Anything else? Anything else? I don't think so. Okay. So I'll take a 5 minutes break from you. I will come back. Okay. Please give me 5 minutes. Then about this digital electronics. So we have analog electronics and digital electronics. So far you have used several ICs in your labs, like logic IC, JK flip-flop, all the ICs. But all those ICs inside the IC, although you are performing the digital electronics, that means zeros and ones, but we need to design all of those circuits by using the analog circuit, right?
Yeah.
Like a RTL, TTL, resistor, transistor, diode transistor logics. So we'll move there, and most of the sensors that we talk about nowadays is actually sensing the continuous signals from the nature, like a pressure, like temperature, anything else, but that we need to process it inside the processor. Inside the processor, it is a digital electronics. So before processing, we need to do some conversion. That means from analog to digital conversion, then digital to analog conversions. So we'll move there, analog to digital conversion, digital to analog conversion, the circuit detail. But at the beginning, we just want to understand about the basic things. Maybe most of you actually have those ideas, but I want to just refresh the memories here. So this is the codes, binary codes. That means in binary, we have only 2 digits, right? Either 0 or 1. Everything in digital electronics we represent either by 0 and 1s. In the analog, we have a decimal numbers from 0 to 9. So how we can represent those things? There are some techniques to represent those decimal. Like one of them is the binary codes. It is a way of representing letters, characters, and numbers using group of 1s and 0s. If I go fast, if you cannot understand my pronunciation, please let me know. Okay? So binary codes which are used to represent the numeric information. This is binary codes. It can be either numeric or alphanumeric. If it is only numeric, that means we are using the codes to represent the numbers only. If it is alphanumeric, we want to use the codes like characters, the alphabets, and the numbers. So most commonly used alphanumeric codes are the ASCII code, right? The ASCII code that you use to send information from our processors to the I/O device, like a printer, like a mouse, keyboard. They use the ASCII code. So the most commonly or basic binary code decimal is the 8421. 8421 is a weighted code. So in the BCD binary coded decimal code, each decimal digit is encoded into a group of 4 binary digits. So we already mentioned that in decimal we have how many? Decimal 0 to 9. So we have to represent it in binary because we have to process inside the processor in the digital form. So we need to convert it from the analog to digital. So we can do that by using the BCD code. There are 3 different kinds of BCD code. One is 8421, 2421, and 5421. Those are known as weighted code. Why they are known as weighted code? Because they obey the rule of position weighting principle. Position weighting principle. Each position in the number has some specific weight. How it will work? Let's see. So for example, this is the 8421 BCD code, and we have a decimal number from 0 to 9. And how we actually arrange this number? We actually arrange this number, if you take the summation of each weight, then it will represent the equivalent decimal number. For example, if you look at here, so this is the weight. As I mentioned that they are maintaining the principle of position over weight. So this is the position of the weight. So this is 8, this is 4, this is 2, this is 1. the weight of this position is 1, the weight of this position is 2, the weight of position is 4, the weight is 8 here. So for example, if you want to get the decimal number of 4, you just add the weight of the position which has logic 1. So this one. So here we have only 4. We don't have to count these two things. 0 plus 0 is 0, no problem. So if you take this one, so 1, 1, 1, so 4 plus 2 plus 1. 4 plus 2, 6, 6 plus 1, 7. So equivalent to 7. If you sum the weight, it is 1. So 8, only 1. If you add the summation of this position, 8 plus 1, 9. So this is how it works. So this is known as BCD code, 8421. So we have 3 different kind of BCD code. Out of that, 8421 is most widely used. We have also 5421. It's same. If you just add the weight of the position, then you get the equivalent decimal number. In case of 5421, if you just this one, 5 plus 1 is 6. 4 plus 2 plus 1, 7. 5 plus 2 plus 1, 8. 5 plus 4 equals to 9. So that's why it is known as weighted code. It will give you the weight of the position according to your binary position. Okay. There is also a negative weighted code. In the negative weighted code, it is 8, 4, minus 2, minus 1. So it will be same. So you have to get the summation of the weight of each particular position when there is a 1. So for 1, it will be 4 minus 2 minus 1. So you will get. For example, if you want to choose the 6, so 8 minus 2, 6. For this one is 8. For this one, 8 plus 4 minus 2 minus 1. 8 plus 4, 12. 12 minus 2, 10 minus 1, 9. So this is how the BCD code works. Okay. Then we have non-weighted code. There are 2 different kind of non-weighted code. One is access tree, another is the gray code. And also we can see there is a sequential code. This gray code is also known as sequential code. What is the sequential code? If you just add 1, you will get for the next equivalent code. If you just add 1, you will get this code. If you add 1, you will get 1. So 0, 0, 0 plus 1 will give you 0, 0, 0, 1. Then if you add 1, it will give you 10. If you add 1, it will give 11. I know you already know how to add the binary data. So this is known as sequential code. Gray code is also known as a sequential code. That means in the gray code or in the sequential code, at a time only 1 bit is changing. Only 1 bit position is changing. This is important. The gray code is important because in the gray code and the BCD code there is a difference. In the BCD code, it is possible to change 3 bits at a time. But in the gray code, only 1 bit position will change. Okay. And what about this access tree code? If you add binary BCD code 3, binary add 2 to 3 to the any BCD code, it will give you to the access tree code. Okay? It will give you the access tree code. Out of these 3, most of the important for us is the gray code because we will see in future that gray code is using in some circuitry. Okay. The sequential code is also BCD 8421 or access tree is also known as the sequential code. So if you look at here, this access tree and gray code is non-weighted code. That means if you add the weight of this position, it will not give you the equivalent number. That's why they are known as non-weighted code. Okay. Then the cyclic code. Cyclic code, the successive code differs from each other by only 1 bit position. Same successive code, gray code is differ by only 1 bit. Okay. So I'm just going through very fast because it's not required for our, just refreshing our memory, right? Then we have the self-complementing code. What is this self-complementing code? If you take the complement of 0, it will give you decimal number 9. If you complement the decimal number 1, it will give you 8. So this is known as self-complementing code. That means 9 complements of the decimal number 3 is equal to 6. code of the decimal digit 3 is 0, 1, 1, 0. So if you look at here, 0, 9. So it is 0. So if you, sorry, not this one, this is 8421, this is XS3, this is decimal. Then if you just take the complement of 0, 0, 0, 0, it will be 1, 1, 1, 1, so it will be 9. If you take the complement of 1, that means 0, 0, 0, 1, that means it will be 1, 0, 0, 0, so it will be 8. So these are known as self-complement. Now, okay. Then we have this most important codes, this error detecting and error correcting. Because in any communication system, we have to transfer the signals, right? In analog signals, we transfer the analog signals. But in the digital communication system, we have to transfer only bits, 0 and 1s. So the transmitter will transmit the signals and it will pass through the free space, or it can pass through the waveguide, right? Like an optical fiber. Or we can send data by using the microwave antenna, and the receiver will receive the signal. But in between transmitting and receiving, anything can happen. That means a noise can generate, a noise can be added, and bit can be flipped. You are sending 1, 0, 0, 0, maybe the receiver will receive 0, 1, 0, 0. So if any bit can be flipped, the information will be altered, right? So this is called noise. So we have to have the ability at the receiving end to detect that error, and also have the ability to check and replace that error. So this is known as error detecting and error correcting. So this is most important course that we need to understand. Okay. So as I mentioned, so for example, if you look at the 8421, this is 8421 from 0 to 9. For example, we are trying to send decimal 4, which is equivalent to 0, 1, 0, 0. But at the receiving end, we are receiving 0, 1, 0, 1, which is equal to 5. Though we are sending decimal 4, we are actually getting decimal 5. So this is an error. So at the receiving end, we have to have the ability to detect that error. And by using a bit is known as parity bit, is called error detecting. Okay. So we will discuss more in details about this error detecting and error correcting. Okay. Let's start with this gray code. Why it is important? If you look at here in the 4-bit binary code, BCD code, when we change it from here, from 3 to 4, 3 bits are changes, right? 1 to 0, 1 to 0, 0 to 1. Or if you go from 7 to 8, all the 4 bits are changes. So if we want to implement or design a sensor, a position sensor, and you separate them each logic block by 3 cores, for example, from 0, 0 to 1, 1, 1, and the ball is shifting from one place to another. So if our bits is not changes properly, then we cannot detect the proper position. So if it is a PCD code, if you use a PCD code, it will give you a valid code. Even it is changing 3 bits at a time, it is actually giving you a valid code from 7 to 8. But if you look at the gray code, as the gray code will change only 1 bit position at a time, so it is very easily determined, or easily it's possible to detect its position more precisely. So that's why we can use this gray code for position detection. So this is particularly useful in the position encoders. Position encoders are used to track the linear and angular position of the objects. For example, so A, B, C are 3 position sensors. So we have 3 variables. So we have from 0, 0, 0 to 1, 1, 1. So we can define 8 different locations from 0, 0, 0 to 1, 1, 1, from 0 to 7, right? 8 different locations. Now the ball is moving from 0 to 1, 1 to 2, 2 to 3, like this. So when the ball will move from 0 to 1, only 1 bit is changes. It is from 0, 0, 0 to 0, 0, 1. Reader can understand, no problem. Then if you move to 0, 0, 1 to 0, 1, 0. 0, 0, 1 to 0, 1, 0. We have 3 different sensors, A, B, and C. If any of the sensor can be faster or can be slower. So for example, if sensor B is little slower, then see what will happen. Still, though the ball moved from 001 to 010, we can sense it is 000. Though the ball at position 2, the reader will get information the ball is at position 0. Because all are valid information. 00 is also valid in BCD code, 001 also valid. Or if the sensor C is little slower, then it will be 011. So though the ball is at position 2, the reader can detect either it is at 0 position or at position 3. So this is the problem. Okay.
Can you explain it again?
Okay. So A, B, C. So we are at position 0, 0, 1. In the next time cycle, the ball is supposed to go to 0, which position? 0, 1, 0. It's supposed to go 0, 1, 0. So these are all sensors. The sensors is may possible because it's a mechanical thing, right? It may possible that sensor B is little faster, sensor C is little slower, anything can happen. So what are the two basic problems can happen if sensor B is little slower? If sensor B is supposed to go from 0 to 1, right? But if it is slower, it will remain still in 0. So they are all in 0. They will move to this position. So it's supposed to go to position 2, but it's saying that it is still at position 1.
Okay.
Or it can be happen that it will go to 0, 1, 1. Or it can be possible that it is more faster. This is changing. This is more faster. It will go here. It is position 3. It is still at position 1. Or it can happen also. It can go 0, 0, 0. Why this problem? Because here 1 to 0, 0 to 1. Two bits are changing. In the BCD code, it is possible to change all the bits at a time. But in the gray code, only one bit position will change. That's why it is easy to implement any position sensor by using the gray code. So look at here. So either the ball is supposed to be here, but it can detect either ball is here or the ball is here. So it will be more O's. If you look at here, when it is going from 0, 1, 1 to 1, 0, 0, it is transmitting from 1 to 0, 1 to 0, 0 to 1. So all the three sensors are changing now positions, right? So it can be what it can happen. It is going to 1, 1, 1. If any of the sensor is slow, for example, sensor A is faster, so it will go from 0 to 1 before they go from 1 to 0. So at some moment, it will show at 1, 1, 1. But the ball will be at 1, 0, 0. So these are the possible if you implement a position sensor with a BCD code. But if you want to implement the same thing with the gray code, what will happen? In the gray code, we already know that one bit position will change at a time. So now, we will not have to worry here. From 0, 1, 1, it will go to 0. So 0, 0, 1, 1, only one position is changing. So every time, only one position is changing, if you look at here. So the gray code is very important to utilize in the position sensor. So these are some. So we can say error is minimized here. Okay. It is also used in the digital communication as well as angular position detection. It's great. So important thing is how we can get or how we can convert this binary to gray code, or we can get the gray code to binary code. So this is the technique to convert the binary to gray code. So in this column is the binary code. It is an A421 BCD code from 0 to 15. So it's a 4-bit combination from 000 to 1111. And this is the gray code. To convert the gray code, the system is So this is the MSB, right? Most significant bit, MSB B3, then B2, B1, B0, the LSB, least significant bit. Write down the position for the gray code, similar, G3, G2, G1, G0. G3 is the MSB and G0 is also. To convert from binary to gray code, at first, the MSB will be the same, B3 equals to G3. Whatever the value of B3, it will be the same for G3. Then for this G2, it is B3 XOR of B2. I hope you can remember the XOR, but we will discuss later. The XOR is, the output of XOR will be high or 1 if both inputs are in opposite. If both inputs are in opposite, the output of XOR gate will be high. High means 1, logic 1. High means logic. So if we have two inputs, how many combinations we supposed to have?
0, 0, 0, 1, 1, 0, 1, 1.
So output of this XOR gate will be high when both inputs are opposite. That means 0, 1, 1, 0.
1, 1.
If the both inputs are same, the output will be 0. This is XOR. So to get this G2, we have to take the XOR of B3 and B2. To get the value of G1, so B3 XOR B2 of G2, G1 equals to B2 XOR B1, and G0 equals to B1 XOR B0. So this is the simplest way. So now if you look at it, so B3 equals to G3 equals to 1. What about G2? It is B3 XOR B0. So 1, 0. 1, 0 means 1. Then G2 equals to G3 equals G1 equals to B2 XOR B1, 0, 1 will be 1. Then G0 equals to B1 XOR B2, 1, 0, 1. Simple. Okay. So what about this one? 0, 1, 0, 0. So very simple. So this is B3. So G3 will be same. Then for G2, this one XOR this one. So 0 and 1, 1. Then for 2, 1, 0, 1. For 0, 0,
0.
So if you just can remember this diagram, it's very easy. So B3 will be directly equivalent to G3. G2 will be this 2 XOR. Then this 2 XOR will be here. Then G2 XOR will be here. Okay, this is binary to gray. Because most of the cases, it's simple, we use this binary code, BCD code, 8421. Then we need to convert it to different kind of codes. What about, yeah?
Are you going to post these slides to Canvas?
I didn't? Sorry. I uploaded, but I forgot to publish it. Just make it now. Thank you. So if I forgot, please give me a reminder. I supposed to publish before coming here. So now this is for binary to gray. What about gray to binary? Simple. Again, that means you have the gray code, you have to convert it to the binary code. Okay. For example, this gray code is given. Now you have to return it to the binary code. For example, this 1, 1, 1, 0. Same. The MSB of the binary code and the gray code will be the same. The MSB of the binary code and gray code will be same. So here B3 equals to G3 equals to 1. What about the next code? For B2, it is B3 XOR G2. Diagonal. B3 XOR G2. For B1, it is B2 XOR G1. For B0, it is B1 XOR G. So
Diagonal.
this is the diagonal. So G3 is equivalent to B3, then this diagonal. And XOR is, the output of XOR gate will be high when both inputs are opposite. When the inputs are opposite. If the inputs are same, you will get low. Okay, so this is all about the gray code. Now I'll move to the next slide about this error correcting and error detecting code. Okay. So in the error detecting and error correcting code, as I mentioned, we are transmitting a signals, a binary digits or digital signals. In the digital signals, we will just send zeros and ones. And it is very much possible any of the bits position can get altered. You are sending ones, they will receive zero. You are sending zeros, they will receive one. It's very possible. But important thing that we need to find out the way to detect it and to correct it. If you want to detect it or correct it, we need to add extra bit that is known as parity bit. That's why known as a parity checker as well. Okay. So additional bits are sent along with data bits. Of course, it will increase our bandwidth. But with the cost of bandwidth is better for us to get a errorless data. Okay. So parity bit and parity checker. So from the transmitting side, we will add a parity bit. In the receiving side, there will be a parity checker. In the transmitting side, it is known as parity bits. The extra bit we have to introduce, we have to generate. Actually, we have to generate parity bits according to the codes. In the receiving side, we have to find out the parity checker. Okay. So in the receiver side, we can have parity checker, CRC checker, checksum. So most of the cases, we actually use the parity checker. So for example, this is a data bit, and these 3 bits are additional bits is known as parity bits. 3 bits, 1 bits, 4 bits, whatever it is. So these are known as parity bits. These parity bits can be even and odd. This parity can be even or odd. What about even and odd? The number of ones you are sending. Number of ones that you are sending. Are you sending 3 ones? Are you sending 5 ones? You have to calculate. So if we are sending even number of ones, it is known as even parity. If you want to send odd number of ones, it is known as odd parity. And ones including the parity bit. That means there are 2 different things. One is data bits that you are sending. For example, 1010. 1010. I want to send this one. 1010. This is my data. I want to send it. And in the receiving end, I need 1010. Okay? So, if any bit is altered, everything is changed. So here we have even number of ones, 2 ones, right? If you want to make an even parity, then additional bit will be 0. Because still we have even number of ones. If you want to make an odd parity, as the number of ones is 2, we need 2 parity bit will be 1. So that overall code will be even number of odd number of ones. This is how the parity bits will be generated. So before going to more details about the parity bit, there was a design. Okay, they are talking about these things. Number of ones in the code, including the parity bit, should be even. Think about even. So 1, 2, 3, 4, 5. So odd number of ones. So we should add 1 here. So 1 here. 1, 2, 3, 4, 5, 6. So in this case, 1, 2, 3, 4, 4 ones is here. So we don't need to add any parity bits. Parity bits will be 0. So this is our even parity. Okay. So in case of odd parity, the parity bit should be 1. So this is even parity. This is odd parity. Here, if you look at here, 1, 2, 3, 4. It's supposed to be odd number of ones. That's why we add 1. So this is called odd parity. In this case, even parity, 1, 2, 3, 4. So we have already 4 ones. We don't need to add any parity bits. The parity bit is 0. Okay, fine. Now, for example, this is our code. This is total code. Data bits, plus parity bits. We send it. Which one we send actually? This one, right? 1110, this one, yeah. We send it and the receiver received it. But we can see here there is an error. We're supposed to send 10, here we are receiving 01. In the receiving side, the parity checker will check, as of course there will be an agreement between the transmitter and receiver. What type of parity we are using? It's not like that the transmitter is working on even and receiver is working on odd. They're supposed to have some good agreement between them. If the transmitter is sending even parity, the receiver also supposed to check the even parity. So for that case, this is even parity. That means transmitter is sending even parity. In the checker side, they will also count the number of ones. Here the number of ones, how many? 1, 2, 3, 4. So 4 even. So this is an error. So in case of odd parity, the parity bit should be 1. And the receiver parity should be odd, but there is an even number of, right? So parity checking circuit will detect this error. In case of even parity, the parity should be 0. And the receiver parity should be even, but here is odd. So if you send even parity, the parity checker will also try to find the even parity. If you send the odd parity, parity checker will try to get the odd parity. If they have any difference, they will detect the error. This is only detecting error. They are not able to correcting it. They just detect there is an error, nothing else. Even they don't know, yeah.
What if you have 2 bits flip and it provides?
Will come.
Okay,
Yeah.
that'll come.
This is very sequentially.
Okay.
At first we thought that at this position we can just only identify the error. Still we cannot correct, even we don't know which bit actually flipped, which position actually flipped. Even we don't know that. We just know that in total data that we receive at the receiving side, there's an error. We don't know whether this bit or this bit or this bit, which position have flipped. We don't know. And it is only for 1 bit error. Yeah, of course. Okay. So now your question. If there are more than 1 error, okay, so the error can be also happen like that. It can be, if more than 1 means 2 error can possible, 3 error can possible, 4 error can possible, 5 bit error can possible. If it is 2 bit error or 4 bit error, we call it even error, even bit error, even position bit error. If there are 3 bits error or 5 bits error, we call it odd position error. More than 1. We are talking now about more than 1 bit error. So 2 bits can be flipped, 3 bits can be flipped, 4 bits can be flipped, 5 bits can be flipped like that. So if the number of errors are even, we call it even error. If the number of errors are odd, we call it odd error. Now, with this parity bit, there is of course a drawback or the limitation. If there are more than 1 error or even number of errors in the code, we cannot detect. This is the drawback. The parity bit cannot detect even number of errors. So for example, we are sending this data. So 1, 2, 3, 4, 5, 6, 6 bits data. Okay. So we have 1, 2, 3, 4. So for example, we are trying to odd parity 1, 2, 3, 4. So we are talking about odd parity. Okay. Odd. So our parity bit was 1, 2, 3, 4, 5. So we need to make it 5. Then we send it. We are receiving 1, 0, 0, 1, 0, 1, 1. 1, 2, 3, 4, 5.
Still it's on.
We are sending 5 is to 5. But there is flipping. How many bits flipped? 2 bits position is flipped. That's why it's not possible to get. If the number of errors are even, the parity checker cannot detect the errors. This is the drawback or the limitation. If we have odd number of errors, it can detect. If we have odd number of errors, it can detect. If we have error of 1 bit, it can detect. If we have error of 3 bits, it can detect. If we have error of 5 bits, it can detect. If the errors are in odd number, it will detect.
So,
Yeah.
using odd or even parity
Both
is
cases.
based on our choice, right?
Yeah,
Okay, sir.
based on the designer choice.
Yeah.
The company, the engineer, they decided, okay, we'll use the even parity.
Yeah.
But we have to have agreement between the transmitter and receiver
Transmitter
side.
and receiver.
They should have the same page. Okay, so once we decided, okay, fine, we'll use the odd parity.
Okay.
So that means every time we'll try to give even odd number of ones. In the receiving side, they will also check, try to get odd number of ones. That is called odd
It's the
parity.
same process.
Same process. But problem is error.
Error, yeah.
If the error is even, we cannot detect.
Yeah.
If the error is odd numbers, we can detect. Any confusion here? So parity bit can only detect odd number of errors in the receive port. This is very important. So for example, we talk about this is for even parity. This is even parity cases, right? Same thing for odd parity. This is true for odd parity too. In case of odd or even parity, if there are even number of errors, the parity cannot detect the error. If there are odd number of errors in the receiver code, then using the parity bit, it is possible to detect the error. Okay? Okay. Now, as I mentioned, it is very initial stage. We just find out a way to detect an error, but still, it is not possible for us to correct the error, or even to find out the position at which position the bit actually flipped. But once the error is detected, the receiver sends an acknowledgement to the transmitter and asks for the retransmission of the same data. Okay, I received wrong data. They can send, acknowledge, hey, I received the wrong data. I supposed to receive even number of ones, but I'm receiving odd number of ones. Please resend me. But it is always not possible. For example, if it is a satellite communication, for satellite communication, you are sending data to satellite, then it will ask you again, hey, I'm receiving the wrong data, please send me again. So it is a waste of money. It's an inefficient method. So we need to find out a way that the satellite itself can detect the problem and correct the problem. Okay? Or for example, you are using a Bluetooth, excuse me. You are using a Bluetooth. You are sending from one phone to another phone. So if the data is wrong, then they need to send it back. Then they need to cover it back. But if so it is not always possible to retransmit or recorrect it. So here we cannot detect the position. Here we also can't correct the error in this parity chain. To improve this one, the next error correcting code is known as Hamming distance. Hamming distance. Okay. So we already discussed about these things. Now we are trying to find out a way for correcting. This is known as error correcting code, ECC. Error correcting code. Okay. Why we need this ECC? As I mentioned, if it is a satellite communications, it's a multiple communications, if it is a memory devices, it's not possible for them to ask them retransmit the information again. So how we can try to find out a way? As I mentioned, there is a way, it's called Hamming distance, but before going to the Hamming distance, there is one simple another technique, is the repetition. The repetition code means you want to send one, but you are sending 3 ones. You want to send only 0, instead of 1 0, we need to send 3 zeros. And on the receiving end, they will try to find out the majority number of bits. Is it majority ones or majority zeros? For example, we are sending 1 1 1 for single one, and the receiving side, though there is an error, 1 gets flipped, but still the 1 1 is the majority. So it will sense 1. Okay? But this is another inefficient way, right? Because you only need to send 1 bit, but you are sending 3 bits. So totally inefficient. Because in real life, it's not about 3 bits. It's a millions of bits we need to send. So it's an inefficient way. Even if the 2 bits get changed, 2 errors, now we are sending 1, we are getting zeros. But to improve that one, even they cannot understand there is an error. To improve that portion, we actually increase the number of bits. Now we are sending 4 ones for only sending 1 ones. Again, 2 bits change errors. Now what happening? They are trying to get the majority ones, but there is no majority. Then they said, okay, I didn't find any majority, so there is an error. They are not telling that we can correct it, they can detect the error. But still, it's an inefficient way. Okay, this is known as repetition mode. So by increasing the number of redundant bits, it is possible to detect and correct more errors, but it's an inefficient way. So what is this Hamming distance? The Hamming distance is the number of bit position at which 2 codes differ. The Hamming code or Hamming distance is the number of bit position. Number of bit position. We have the position, right? Position, weighted position, 8421. So that means this is LSB and this is LSB. So 8421, like this, right? The position weighting. So Hamming distance is the number of bit position at which 2 codes differ. For example, you are sending 1011 and the receiver is receiving 1101. So we have a change of, it flipped from 0 to 1, it flipped from 1 to 0. So this Hamming distance is 2 here. In this case, how many bits change? Flipped 3 bits. So it is called Hamming distance 3. Okay. So Hamming distance will give you how many bits are changed, how many bits are flipped. Okay? So Hamming distance between these 2 cases is 2, Hamming distance between these 2 codes is 3. Why it is important in Hamming distance? Because if you look at this 8421 BCD code from 0 to 9, from 0002 to 1001, the minimum Hamming distance is 1. What is Hamming distance? How many bit positions changed? How many bit positions changed? So here 00000001. Hamming distance 1. In this case also 00001101. Hamming distance 1. So this is the minimum Hamming distance. So for BCD code, minimum Hamming distance is 1. Okay. So if the error happened and it take it to a valid code, both are valid. Though you're sending 2, they are receiving 3. You are sending 0, they are receiving 1. Both are valid code. So this is the Hamming distance. So in the BCD code, it is the smallest Hamming distance between all possible ports in the given encoding system. So for BCD code, minimum Hamming distance is 1. The maximum Hamming distance is which one? 4.
7 to 8.
0, 1 to 0, 1 to 0, 1 to 0, 0 to 1. This is the maximum Hamming distance. So by error, if there is a change, even 1 bit, then it will lead us to a next valid code word. This is an error, but valid code. It's not like an invalid code, but this is an error. So if you use the BCD code, even 1 bit change, it will lead you to next
Valid.
valid error code. Valid error code. So this is the very clear what is Hamming distance?
Yes, sir.
Okay. So what about the repetition code? In the repetition code, what is the minimum Hamming distance? 3. Because we are sending 000 for only 0. We are sending 111 for only 1. So what will be the next valid code? 000 to 111. So minimum Hamming distance is 3. Because all the 3 bits need to change. 0 to 1, 0 to 1, 0 to 1. In the repetition code, the Hamming distance is 3. But here, how many bit can correct? Only 1 bit correction. So in the repetition code, minimum Hamming distance is 3. That means unless all the 3 bits get flipped, we will not reach to the next valid code. Important is valid code. So this Hamming distance tells us that how many number of bit flips will lead us to the next valid code. If it is lead us to the invalid code, it's no meaning. Important is the next valid code. In digital communications, in digital electronics, all are follow some rules. Either it will use 8421 BCD code or 5251 BCD code or the gray code or the access3 code, right? And they have the proper list. So they know what is the valid code. So we need to, whenever there is a flip and it will reach to a next valid code, that is the error. Okay. So there is an equation we need to find out for error detection and error correction. The equation is minimum Hamming distance d min equals to d plus 1. And to find out the correction, to get the correction, minimum Hamming distance will be 2d plus 1. What does it mean? It means if we want to detect d number of errors, then minimum Hamming distance is d plus 1. Okay? And if we want to correct d number of errors, then minimum Hamming distance is 2d plus 1. So for 1 bit error correction, so look at here, for 1 bit error correction, which one? 2 into 1 plus 1, 3. That is the repetition code. And in the repetition code, we can correct only 1 bit. Can correct only 1 bit. Okay. So of course, this is very inefficient process because we are trying to send only 1 bit, 1, but we need to send 3 ones. The efficiency is how much? 33% only. Only 1/3, right? 1/3. By sending 3 ones, actually we are trying to send only 1 once. So efficiency is only 33%. So this is the very initial stage. We don't use that one now. So we'll move from the Hamming code now. Okay. So in the Hamming code, we have to add some extra bits. Why you are talking about all those things? Because for error detecting and correcting. And any extra bits is known as parity bits. In this Hamming course, there are 3 parity bits. 3 parity bits. Those are extra. We have to send the information. In addition to the information, we are sending extra bits so that we can detect as well as correct. If I want to send only parity bit, we can detect only. We cannot correct. Now we are trying to also correct as well. That is known as Hamming code. Before the Hamming code, we move to Hamming code, we try to understand what is Hamming distance. Hamming distance will tell us how many bits are flipped, how many bit positions are flipped, the bit position. So the Hamming code, extra bits, not only bit, extra bits, because it is more than 1 bit, are parity bits instead of same bits. Okay. In case of repetition code, by adding extra bits, we can correct more number of errors, of course. But it is not so efficient because for sending even 1 bit of information, 2 redundant bits are set. Or for 1 bit of error, correction, 2 extra bits are set. Okay. So, parity bits represent the parity of the certain bits in the overall code. As I mentioned, now we are not talking about only parity bit, it's a parity bits. And parity bits represent the parity overall code. We already know there are 2 different kinds of parity, even parity or parity. Now all these parity bits will represent overall parity of the code. So for 1 bit of error correction, how many parity bits are required in this Hamming code? Let's try to understand. For example, we are trying to send m data bits. We are trying to send m data bits. In case of m data bits, so m is my data bits. Then we need to add parity bits as well. N is my parity bits. So total length is n. If I say that total length is n, total length is, oh, they mentioned k now.
N.
K is my parity bit, right?
Yes.
N is the total length. N equals to
K plus
m plus.
K.
This is the total length. So if I make a block of this one, for example, 1, 2, 3. So this is the total length, n. Here we have both the data bits or information as well as this correcting bit, the parity bit. How we use the equation? The equation is, so as there are total n, 1, 2, for example, I take 7. 1, 2, 3, 4, 5, 6, 7, or n bits. That means it is possible any of the bits can flip. So number of possibility of getting error is n bits. This can be error, that can be error, here can be error, any one can be error, right? So in the n bit of code, total n number of signal bits error can occur. So k parity bits should be able to detect this n different errors, right? This k, we are using this k to detect the number of errors as well. So it has to ability to detect the errors in this n number of bits. They should also be able to identify the state of no error also. We have to identify that there is no error as well. Because whenever you send an extra bit, then every time we need to send an acknowledgement that there is no error as well. So overall, the equation is 2 to the power k supposed to be greater than n plus k plus 1. So if it is like that, if we think that we have 4 bits of data, then we have parity bit, right? So at first we think k equals to 1. So 4 plus 1, right? 4 plus 1. So k equals to 1, right? 2 to the power 1 means 2. So it's not possible to give 4 bits of data. 2 to the power 2 equals to 4. We can send 4 bits, but we cannot add parity bit here. 2 to the power 3, 8. Now we can send 4 bits of data. So for example, this is D3, D2, D1, D0. Now we have left how many bits?
3 parity bits.
That's why the parity bits is 3 actually. We are not sending 1 bit of parity, we are sending 3 bits of parity. 4 plus 2. And the equation is what? N plus k plus 1. So n is 4, k is 3, plus 1.
8.
So plus 1, why? As I mentioned, for correcting. Now we are trying to detect as well as correct. The Hamming distance for detecting is d plus 1. The Hamming distance for correcting is 2d plus 1. Hamming distance for correcting, one is detecting, another is correcting. Hamming distance for detecting is d plus 1. Hamming distance for correcting is 2d plus 1. So plus 1 is for correcting. So here, why I mentioned these things? For example, just an example, I chose a 4 bit of data. To transmit a 4 bit of data, we need 3 bits of parity bits. Why? Because it is k. So if we want only 1 bit of parity, it is only 2. We cannot send 4 bits of data. If you choose 2, it is 4. You can send only the data. You cannot send the parity bits. If it is 3, we know now we have 8 bits. That's why. So look at here. So n equals to 4, k equals to 3. Now I'm coming to you. How we choose the bit position for the parity? If you can see in the example, I just don't mention D3, D2, D1, D0. I keep this left. This position is for parity bits. How? Because now we have 3 bits, parity bits, right? We have 3 parity bits, P1, P2, and P3. So we need to put in specific position. How we decide this position?
So P power 0,
Yeah.
P1 power 0, P2
So it
power
is 2 to the
1,
power 0, it is 2 to the
2
power
power
1,
1,
it is 2 to
2
the
power
power
2.
So 2 to the power 0 means 1,
1.
to the
Two.
sorry, 1 or 0, what they mentioned, P1, it is P2,
P2
it
and
is,
P4.
that's why we put it. So this is P1, this is P2, this is P3. That is how, so we need to, it's not like random, that you just, okay, I put P1 here, I put P2 here, no. There is a specific equation how you decide the position for the parity bit as well. So if you have 4-bit parity, it will be P4
to
to the
power
power
3. 8.
So whenever you have P4, that means 2 to the power 4, 16. Right? If I'm not wrong, 2 to the power 4, 16, yeah? 16. So 4 for parity, 12 for data. So 12 data bits you can send. So if you increase the number of bits information, you have to increase the parity bits as well. Then you have to choose according this way. Then you have to choose the position for parity bits according this way. These are the position, how we choose the position. This is the value, how many numbers of parity we require to send. So here it is 4. So if it is 5 bits, can you send with this one? No. So we need to go to the next level. Okay. So this is known as 7-4 Hamming code. Why it is known as 7-4 Hamming code? Total length is 7 bits. 4 bits is for information or data. We are sending 7 bits. Out of 7 bits, 4 bits are information or data, and 3 bits for parity bits. So it's known as 7-4 Hamming code. Okay. So how we will choose this P1 value, P2 value, and P3 value? As I mentioned, this parity supposed to be the parity of overall code. If I read this one, this parity bits, that means P1, P2, and P3, represent the parity of the certain bits, not overall bits, certain bits in the overall code. How we decide? Let's see. Now we are trying to find out. So it is, data is not that we are generating ourselves, right? That is there. For example, whenever we talk through a mobile phone, our voice is our data. So data is automatically there. Now the system will generate these parity bits. They will add it to my voice so that in the receiving end, it can detect and make sure that it is errorless. So how we can generate these parity bits? So we have 3 different kind of parity bits for this 7-4 Hamming code. For the 7-4 Hamming code, we already know that in the 7-4 Hamming code, 7 is the total length. Out of that, 4 bits of our information or data. 4 is information or data. 3 is my parity bits. 3 parity bits, right? P1, P2, P3. Okay. And we are getting from 2 to the power 3. That means 8 combination. So 0, 0, 0. So it's, for me it's easy to remember. Okay? So P1, P2, P3. From the table, because in digital, everything about truth table. You have to make all the logic, all the equation from the truth table. So we have 3 bits of parity. So 3 bits parity means from 0, 0 to 1, 1, 1. From here, from this truth table, we will generate the value of P1, P2, and P3. So P1. P1 represents of all bit positions whose LSB is 1. P1 represents the parity of all the bit positions value which LSB is 1. Which is the LSB? This column is the LSB, right? This column is the LSB. We have 1 here, 1 here, we have 1 here, we have 1 here, right? So this is how many? Look at here: 1, 2, 3, 4, 5, 6, 7, 8. 0 to 7, right? 1 to 7. So 1, 2, 3, 4, 5, 6, 7. So P1 itself is there, 1. So if we are to take an even parity, for example, P1 is already at even. Now we need to take an even position. 1, 1, 1. So 1, 2, 3, 4, even. So we need to take the position of this one. So which is this one? This is B0. Because it is P1, it is P2, for example, it is D0, it is, number 4 is D1, then number D1, P1, P2, D0, sorry, P3, then D1, D2, D3. Or we can say position number 3, 5, 6, 7. This is 0, 1, 2, 3. Position number 3, 4, 5, 6, 7. So if you look at here, P1 will get the parity of 3, 5, 7 even. That means again the XOR gate. You have to XOR, make it XOR. So here it is even, right? So 1, 1, 0, 0, 1, 1, 0, 1, 1, 0. So even if you take the XOR of these 4, it's supposed to be even. So the P1 will get from this value. 1, 2, 3, 4. Even number of ones. Then 4. P2 represents the parity of all the bit position whose second LSB was 1. The second LSB. The second column.
P2.
For the P2. This is P2. So this is for P1. We don't need to consider this one. This one is for P2. Then we have 1 here, we have 1 here, we have 1 here. Which position? 3,
3,
6,
7.
7. So 3 XOR 6 XOR 7. D1 XOR D3 XOR D4. Because in this is D1. If you look at here, this is D1. 1, 3, 4. Oh, they mentioned 1, 2, 3, 4, right? So they didn't mention 0. 1, 2, 3, 4, right? Yeah. That's why we are getting confused. So 3,
6,
6,
7.
7. 3, 6, 7. How much time left? Yes, sir.
Why aren't we counting bit position 2 in P2?
For P2?
Yes. Why are we not counting the first?
This one?
Yes.
This is the P2 itself. And P2 itself is given. If you look at here, bit position 0 is P1, bit position 2 is P2 itself. P2 itself is here. Okay? And we're trying to get an even parity. We put 1. Even. That's what I mentioned. So at first, of course, we need to decide whether we are trying to get an even parity or an odd parity. So for example, we just decide to agreement, we will try to get the even parity. So we mentioned already, even is something. Then we are getting this next position. This one, this one, this one, this one. So this is D1. Then we have D6. Sorry, D3, D4. D3, D4. 3. This one. So position is which one? 2, 3, 6, 7. Or we can say D1, D3, D4. Okay? What about the P3? P3 will be the MSB is 1, the last column.
Yes.
In the last column, so here, this one even, why we don't take in account because itself it is P3. So P3 is even, then this is 3. P3 is even, then D2, D3, D4. So this is how we can generate the parity bits. For example, how much time we left? 5 minutes? 1 minute? Okay. So look at here. We want to send this data bits 1010. So we need to send 1010. So that means we already decided. We want to send 1010. Now we have to find out
P1,
P2, P3. So try to find out P1, P2, P3.
uh,
For P1,
P1
it is
is
3, 5,
5,
7. 0 and 1, 1.
1.
1 and
1 and 1,
1 and 1, 0.
0.
0 and 1, 0 and 1, 1.
1.
So that's why,
P1 is
sorry, 0 and 1, 1. 1, 1,
1, 0. P1 will be 0.
0. For P2, 3, 6, 7. 3, 6, 7 is 0, 0, 1, right? So for 0, 0, 1, 0, 0, 0,
0.
0, 1, 1.
1.
Even. And for last one, P3, what is the P3? Oh, here is the P3, sorry. P3 is 0. So we put our value here, 0, 1, 0. So this is the total data we send. So 1010 is my data, 010 is my parity. So we'll continue from here and we'll move to the logic gates. So these are the parity bits. This is more important for our communications. We need to send every time. So this is how we can generate the parity codes and add and send. We'll see how we can detect and correct in the next class.
So
Thank you.
the parity bits, so each one basically gets designated a specific
Sorry?
position. Each parity bit essentially gets designated